Good evening everyone. I welcome you to the 8th problem solving session of NPTEL course Combinatorics. So today we'll be discussing few problems from graph theory. That few problems from the graph theory that was discussed this week. So let's start. First, so today the format of the session is, so I have selected few problems. So first, before the problems, we'll recall the concepts that will be used in the problem and then we'll solve it. So firstly, so firstly what so here let's recall first acyclic graph or a forest. So we discussed last time what a graph is. Graph is basically you have to give graph is a tuple where you have set of vertices and set of edges. And what is an acyclic graph, or we also call it forest? It is a graph which has no cycle. Tree, as we discussed last time, it is a connected acyclic graph or a connected graph with no cycles. So you can see this the example in this is an example of a graph which has no cycle. So it is an acyclic graph and it is a forest, but it is not connected, so we can't say it is a tree. But we can see if we have a forest and if we look at its connected components, then the connected components of forest will come out to be tree. Because what is the definition of tree? Tree is a connected acyclic graph. So any component of acyclic graph, connected component of acyclic graph will be connected and it is acyclic, therefore connected components of forest are tree. And we have this and we have a very good characterization of tree, which is the following, that a connected graph of on n vertices is a tree if and only if it has n minus 1 edges. And we also due to this, and we can also see if we have n vertices and if we want a connected graph, so minimum number of edges to make it connected is also n minus 1. So in a way, tree is the minimal tree uses minimal number of edges for a connectedness. So now our first question is, we have to show that number of components of a forest equals number of vertices minus number of edges. Okay, so let's solve it. So suppose, so we start with the graph G, which is a forest. Let number of components of G be K. That is, G is a disjoint union of G1 union till Gk. It's a disjoint union and each Gi is connected. And we have seen previously, like we just recalled, that for Gi, number of edges in Gi is equal to number of vertices in Gi minus 1, because Gi is connected, and acyclic, and Gi is a tree. Therefore, if Gi has n vertices, then it will have n minus 1 edges. It will have n minus 1 edges. So now what is the number of edges in G? Since G is disjoint union of these Gi, number of edges in G will be nothing but sum over number of edges in G, sum of number of edges in Gi, where sum is going over each component. That is, I is going from 1 to k, and since each of these Gi is a tree, the number of edges in Gi is basically number of vertices in Gi minus 1, and I is going from 1 to k. And if we open this up, we will get that this is equal to number of vertices in Gi, and since we have k components, we'll have minus k. And now G was disjoint union of all these Gi. So number of vertices, sum of number of vertices in all of Gi is the number of vertices in G. And there is the number of vertices in G minus k, and k we assumed it to be number of components. So we see this result was fairly simple. We get that number of edges in a forest is nothing but number of vertices in G minus number of components of G. So we basically used here that each of the component is tree, and for tree we know that if a tree has n vertices, we have n minus 1 edges. So now our next problem. So now first we want to define what is a spanning tree for a graph G. Spanning tree for a graph G is a subgraph of G, say T, such that this subgraph, since it is spanning tree, we have two terms, spanning and tree. So we are looking at a subgraph T. It has to be a tree, and by spanning we means that this tree should consist of all vertices of G. So spanning tree of a graph G is a subgraph T of G such that T is a tree and it consists of all vertices of G. And we can observe, we know that any tree with n vertices has n minus 1 edges. So if G has n vertices, any spanning tree of G will have all those n vertices, and any tree with n vertices has n minus 1 edges. So we see that if G has n vertices, then any spanning tree of G will have n minus 1 edges. Moreover, the converse is also true. That is, if we have any subgraph of G which is a tree and has n minus 1 edges, or a subgraph G which is connected as well as has n minus 1 edges and G has vertices n, then we can see that it is a tree and it will be a spanning tree because it consists of all the vertices. So we have a nice characterization of spanning tree, which is a tree which is a subgraph of G having n minus 1 vertices is a spanning tree. So now in this example, suppose G is given by this graph. So this spanning tree need not be unique. So this example is basically showing this. So if we are given a graph G, we can in this we are trying to find a spanning tree. So we kind of require a tree. We kind of require a tree which has all the vertices. So the subgraph whose vertices are blue, you can see that it has no cycle and it is a tree, both of them. And this graph had 6 vertices, and we see that both of these trees have 5 edges. Now in this case you see, so a graph here has 2 distinct spanning trees. So now once we know what is a spanning tree, the next question that we are interested in this, suppose we start with a simple graph G, let T be a spanning tree of G, and let E be an edge of G which is not in T. So then we have to show that we can find an edge E prime in T such that if we remove that E prime from T and add the given edge, then we'll have a spanning tree. So this is the question. So in this previous example, so what do we want to do? We have to show that if we have a G is a simple graph, T is a spanning tree of G. E is an edge in G but not in T. Now we have to show that if we after removing this edge, we can find another edge, and we can construct another spanning tree. So in this example, if you see, so this was my spanning tree. If I am taking my edge E to be this edge, so I want to find another spanning tree which contains this edge E and which is coming from the edges of T, but we have to remove one edge. So since we basically have to remove one edge from our earlier spanning tree and add this edge. So how can we do that? So we see that this edge, now if we look at our T and if we add this graph, then we are getting this cycle. So if we want our tree to have this edge, so we also have a nice character. So if we want to have our tree to this edge, then between this vertex V1 and V2, there should be a unique path, because in tree any set of two vertices have a unique path. But in this diagram, in this T plus E, we see we have two paths. That is, we have a cycle. But therefore we can't remove E, because we want E in our new spanning tree. But we can remove any of this edge. If we remove this edge or this edge, only one edge, we'll see we'll get a tree. We'll get a tree, because then the resulting graph will have no cycle, because this was the only cycle, and by removing one edge from the cycle we have no cycle. So we see that resulting thing will be tree, and it will be a spanning tree because the resulting graph will be connected. If from a cycle we remove an edge, connectedness is not affected. So we see that in this we are getting our answer by removing an edge from a cycle which is consisting of an edge E. And now in this spanning tree, suppose we remove this edge. Suppose we want suppose our edge E that we want to add is this. Now we want to construct a spanning tree which have this edge E and is coming from the edges from our earlier spanning tree, which was this tree. And after removing one vertex from this, now if you see, if we are adding another edge, we are getting a cycle again. So here also, if we remove any of these three edges, we'll get the resultant. If we remove exactly one of the three edges, the resultant tree will be a spanning tree. So in this example we are showing this. Now we'll just, what we have done here, we'll just write it rigorously. So E is an edge in G but not in T. Consider G prime, which is T union E. Now you see that G prime is connected plus has n edges. So this G prime cannot be a tree. If it can't be a tree, that means G prime has a cycle. And we know this cycle contains our edge E, because if it does not contain our edge E, then the whole cycle is contained in T, but T has no cycle, so it has to have an edge E. And moreover, say V1, V2, and it also contains an edge in T. So pick edge E prime in T which is contained in above cycle. Now T minus E plus E prime, this will have n minus 1 edges, and we can see that this is also connected. So we can conclude why it is connected, because we had a cycle and we are removing an edge from a cycle, and if we are removing an edge from a cycle, basically the connectivity, so we are removing a path from this vertex V1 to V2, but since we are removing an edge from cycle, there exists a path, the remaining cycle between V1 and V2. So V1 and V2 are also connected and other vertices are not affected. So we see that this will have n minus 1 edge and it is also connected. So T minus T minus E plus E prime, we are adding E and removing the edge E prime. So we see that T minus E prime plus E is a tree, plus it has all vertices of G. So we are done. So we have shown that if we start with a simple graph which have a spanning tree, and if we pick an edge which is not in a spanning tree, we can construct a new spanning tree by just removing one edge from our tree, one edge from T and adding that edge. So now the next problem. So next problem is based on the chromatic number. So first let's set up the definition of chromatic number. So first of all, what is a proper coloring of a graph? Proper coloring of a graph is we have to define a function from vertex set of G to a coloring set such that each vertex is assigned a color. Each vertex is assigned a color from that coloring set in such a way that no two adjacent vertices have same color. So basically, if even V1, V2 is an edge in G, then V1 and V2 has to have different colors. So any such type of coloring where each vertex is assigned some color and no two adjacent vertices have same color is a proper coloring. Now, chromatic number of graph G is the minimum number of color required to properly color the graph. So basically, if we can construct this function, the smallest coloring set required to construct such a function is the chromatic number. Now some example. So we can see the chromatic number of complete graph of n vertices will be n, because if we pick any edge Vi and V, if we pick any two vertices Vi and Vj, since it is a complete graph, they are connected by an edge. And if it has to have a proper coloring, then color of Vi should not be equal to color of Vj. And this is true for any pair of vertices. So each vertex in the graph has to be given a different color. Therefore, we see n minus 1 colors cannot be a proper coloring for complete graph of n. Each vertex has to be assigned a different color, and hence the chromatic number for complete graph with n vertices will be n. Now another thing is chromatic number for an odd cycle. We can always say that chromatic number for odd cycle will be 3. So any odd cycle will look like this. Basically a cycle with odd number of edges. So if this is our odd cycle, so if we have an odd cycle, so each vertex has degree 2 and it has exactly one in vertex and one out vertex. So we start with any vertex and start giving that color. Suppose V1 is assigned blue color, V2 is assigned green color, and alternatively we keep on assigning these color BG, BG. So this was 5 vertex, but in general also we do that. So we'll reach a point when at the last vertex, and since it is an odd cycle, we'll have that V1 will have blue color and Vn minus 1 will have green color. So the last vertex cannot have a blue color or a green color. So we'll have to assign it a different color, red. Say red. So we see that any odd cycle, chromatic number for any odd cycle is 3. And third example is if G is a bipartite graph, we can ensure that chromatic number of G will be 2, because what is in bipartite graph, we can partition our vertex set into 2 sets, say x, y, and all the edges are between x and y. This set x is, so we have no edges in set x, or no edges in set y. So if we assign a color red to x and blue to y, this will be a proper curl ring, because within x and within y we have no edges. So we see that this is a proper curling. And moreover, so see, these example 2 and 3 are related in a sense. We know that if a graph has an odd cycle, or if a graph has an odd cycle, since odd cycle has to have a proper curling, has to have 3 colors, chromatic number has to be greater than equal to 3. But G is a bipartite graph. An equivalent definition for bipartite graph is that it should have no odd cycle. So any graph which has an odd cycle has to have a chromatic number 3, more than 3. But a graph which so any graph which has chromatic number less than 3 has to have no odd cycle. And what are such type of graphs which have no odd cycles? They are the bipartite graph. So we see that this is a kind of an if and only if condition, that chromatic number of a graph is 2. Chromatic number of graph is 2 with more than, say, 2 vertices, with more than 1 vertices, if and only if G is a bipartite graph. And using 2 and 3 we can prove this. So now once we have defined our chromatic, once we have looked at these example of chromatic number, then we have another number associated to our graph, and that is the clique number. So omega G is the clique number of G, which is the order of largest complete subgraph of G. So if we are given a graph G, we look at all the subgraphs of G which are complete, and the largest one of them will give us the clique number. And we can see that chromatic number of G will always be greater than equal to clique number, because okay. Yeah, so I was saying that chromatic number of a graph G will always be greater than equal to its clique number, because if a clique number of, suppose if clique number of graph is n, that means it contains a subgraph which is a complete graph of n vertices, and we have seen for a complete graph we need to have n color. So that complete graph of n vertices will all those vertices has to have assigned a different color. Therefore we see the chromatic number has to be greater than equal to clique number. Now the next concept is a join of a graph. So if G and H are two graphs, then join of a graph G and H, which is G join H, is what we construct is as follows. We take two disjoint copies of G and H, then add all the, so G join H will have to, first of all, step 1 is to take their disjoint copies of G and H, then add all possible edges with one vertex in G and other in H. So this is a join of a graph. So for example, if we have this, if our graph G is this triangle, and graph H is this one edge. So what is the G join H? What is the procedure? So first we take the disjoint copy of G and disjoint copy of H. Then the next step is we add all possible edges. So if this is a vertex, we add it to all the vertex of the graph G. And we do this for this vertex also. So this resulting graph is G join H. And here, see, you can observe here that K2 join K3 is coming out to be K5. So now the question is this true for random Mn? So in the next question we will see the answer. In the next So in the next answer, like in next question, when we'll be solving this problem, we'll prove something using something related to this. But you can also think, like before proceeding to the solution of the problem, you can think about this. If you have complete graph with n vertices and complete graph with m vertices, can we say that join of kn with km will turn out to be the complete graph of n plus m vertices? Is this true? Okay. So the next question is, we are given a graph G whose chromatic number is exactly one more than its clique number, and we have to show that chromatic number of G join G is the clique number of G join G plus 2. So how will we do it? First of all, we see that there is this notion of clique number of G join G. So my claim is, given graph G H, clique number of G join H. This is my claim 1. Given graph GH, join of clique number of G join H is nothing but join of clique number of G plus clique number of H. So let's prove it. Suppose clique number of G is n and clique number of H is m. So first we want to show that there exists complete graph of n plus m vertices, in G join H. That is, clique number of G join H is greater than equal to clique number of G plus clique number of H. So how do we do that? So since clique number of G is n, there exist vertices V1, Vn in n, V1 and Vn in GV, such that graph induced by V1 Vn. So I am using this notation for graph induced by V1 till Vn is Kn, and W1 Wm in, sorry, this is vertices of G, in vertices of H, such that graph induced by these vertices is Km. Then we see that subgraph induced by V1 Vn, W1 Wm in G join H is, this graph is nothing but join of subgraph in V with the subgraph in G with the subgraph of H, and this is Kn, this is Km, and we can see that join of Kn and Km is Kn plus m. Why? Okay. Yeah. Join of Kn and Km is join of complete graph of n vertices with complete graph of n vertices is nothing but join of k n plus is nothing but complete graph of n plus m vertices. Why? So we see degree of Vi. What is the degree of Vi in G in this Kn join Km? What is degree of Vi in Kn joined in? So since Kn is a complete graph, Vi Vi is connected to each of the vertices other than it in n minus 1, and by definition of join Vi has to be connected with W1, W2 and Wm. So we see that degree of Vi is n plus m minus 1, and similarly degree of Wi is also n plus m minus 1, and this can only happen when Kn join Km is Kn plus m. And this example basically shows that because in G it is connected with all the vertices, and by definition of join we are connecting it with all the leftover vertices also. So we see that join of two complete graphs is a complete graph. And once we see that, so our claim so we have constructed a complete graph of n plus m vertices in G join H. Therefore our part A is done. That is, therefore click number of G join H is greater than equal to click number of G plus click number of H. Now we want to look at the other way inequality. So first start with converse. So first start with a complete graph. Let W be a subgraph of G join H such that W is complete. Consider now, let's intersect W with G and W with H. Since W is complete, W intersection G is also complete, and W intersection H is also complete. So W intersection G is equal to some K n1, and W intersection H is equal to some K n2. So now this is a complete graph sitting inside G, and the click number of G was n. So we get that n1 should be less than equal to n, and similarly n2 should be less than equal to m. And what is the order of this complete graph? Order of W is n1 plus n2, which is less than n plus m, which is equal to click number of G plus click number of H. So we see that any complete graph has at most vertices click number of G and click number of H. So we see that click number of G join H is less than equal to click number of G join H is less than equal to click number of G and click number of H. And from both these inequalities A and B, we see that click number of G join H is click number of G plus click number of H. So now we have done this, but we want so our claim 1 is done, but we wanted to show that chromatic number of G join G is clique number of G join G plus 2 if clique number of G, chromatic number of G is clique number of G plus 1. So now we'll do this. So suppose clique number of G is n and let V1, Vn be the vertices. Let V1, Vn be the vertices such that graph induced by this V1 till Vn is Kn in G. Graph induced is this. Now we have to construct join of G. So first of all, these are the n vertices, and what all are the other vertices? So we'll order the first n vertices refers to the vertices coming from the complete subgraph, and then we can have more vertices. Say we have some n plus k vertices. Now we want to construct G join G. So what are the vertices of G join G? So we'll have this V1 till Vn, Vn plus 1 till Vn plus k, and then we'll have another vertices W1 because we have to take two disjoint copy. So let Wi correspond to the vertex Vi in G join G. So we see, so these are the vertices of G join G. Now V1 Vn is complete. Graph induced by V1 till Vn is a complete graph. Then graph induced, hence since we are taking the disjoint copies, basically these are the isomorphic copies of G. Hence we see that this will also be a complete graph. So now if it is a complete graph, we have to show that chromatic number of G join G is the clique number of G join G plus 2. And clique number of G join G we have computed from our claim 1. It is nothing but 2n. So we have to show that chromatic number of G join G is 2n plus 2. Now, so we have to construct a function f from V of G join G to some coloring set, say C. So now first of all V1 till Vn, since it is a complete graph, it will be assigned, let's say we are assigning them color C1, Cn, and each, since it is a complete graph, Ci will have to be not equal to any of these. And W1 till Wn is also a complete graph. So they will also be assigned some color, say D1, Dn for all ij. So this gives us n colors. And D1, Di also should not be equal to Tj because W1 to Wn, the graph induced by it is a complete graph. So it will give us more n colors. And also we can see that this Ci cannot be for any ij. And Ci also cannot be equal to any dj from this. So we have n colors coming from this and n color coming from this. So we need till to color V1 Vn and W1 Wn. We need at least 2n colors. And this is the minimum. But chromatic number of G was n plus 1. So in G, sum of the vertex in Vn plus 1, Vn plus k has a color Cn plus 1 which is not equal to C1, C2 and Cn. Consider minimum proper coloring of G with minimum colors. C1, Cn plus 1 and this. So we see that we need it more color. Now we also have these vertices. So now what color we are assigning to these vertices? We are assigning them color di if, so basically we are replicating the coloring of previous G to the other G. So we have for each color C1, for each color Ci we have a color di. So what we are doing for each, we are replicating the coloring. So if a vertex has a color Ci in the first copy of G, then that corresponding vertex will have color di in the other copy. So FW1 has, if color of Vn plus I is dj. So we had, so how many colors we have? We had these colors C1, Cn which were all distinct. Then we had these color D1, Dn all distinct, are all distinct. Then we also got two colors Cn plus 1 and Dn plus 1. Now Cn plus 1 cannot be equal to any of these colors C1, Cn, and it cannot be equal to D1 and Dn plus Dn also. So this Cn plus 1 is not equal to Ci, I am going from 1 to n, neither Di, because Vn plus whatever, because this vertex whatever the color, so suppose Vn plus 1 had color Cn plus 1, this vertex is associated connected to an edge to each of the vertex in the other copy of G, and similarly Dn plus 1 is also not equal to any of these color, and Cn plus 1 is not equal to Dn plus 1 also, because the Vn plus 1 will be connected to Wn plus 1 because they are lying in different copies of G. So we see we need minimum 2n plus 2 colors, and hence we are done. So we have proved that chromatic number of G join G is 2n plus 2 if chromatic number of G is n plus 1, where n is the clique number of G. Okay. Now the last problem. Okay. So the now last problem is, we are given a graph G sorry, we are given a graph G which is k connected, and S and T are two disjoint set of the vertex set of G which have at least k vertices. Then we have to show that there exist k pairwise disjoint ST paths. By ST paths we mean a path which is starting from a vertex in X and a path which has one of the endpoints in S and other endpoint in T. So we are given a k connected graph. We are given a k connected graph G. We have two sets S and T. We have some vertices here. They are disjoint and they have at least order k. They have at least order k. S, T. So on. And here order S and order T is greater than equal to K. And we have to show that there exists K pairwise disjoint ST path. That is a path starting in S and ending in T. And these paths also have to be disjoint. So whenever we see, we have to find some disjoint ST path. Which theorem comes into mind? Which theorems helps give us the exact count of disjoint paths? Menger's theorem. So let's see. So this question is an application of Menger's theorem. So first let's recall the theorem and then we'll solve this problem. So this is just for sure. So we are starting with a K connected graph. So by K connectedness we mean that if from a graph G we are removing fewer than K vertices. If we are removing less than K vertices, then G remains connected. We can remove any any subset of vertices which are order less than K, then also G remains connected. Then we'll say that G is K connected. Now Menger's theorems say that if we have UV, two vertices in G which are non-adjacent, that means we don't have an edge between U and V, then minimum number of vertices required to separate U and V equals maximum number of UV disjoint path in G. That is, so minimum number of vertices required to separate U and V, that means that a separating set for U and V, which is a subset of vertices of V, such that if we have any UV path, from that UV path at least one vertex will belong to our set S. If we can find such set S, then such set S is called a separating set for U and V. And we are saying, the Menger's theorem is saying, if we are starting with two vertices which does not have an edge between them, that is, which are not connected by an edge, then minimum number of vertices required to separate U and V equal maximum number of UV disjoint paths in G. That is a path whose one endpoint is in U and one endpoint in V. And by disjoint means, we mean that they don't have any common vertex. So once we have recalled these theorem, now the question was, G was given to be K connected, S and T were two subsets of vertices of G such that two disjoint subsets, such that order of S and order of T is at least K. To show that there exist K paths, K ST paths which are pairwise disjoint. Okay. Now as we see earlier, so basically what we have these two sets S, T, and we have some vertices here V1, V2, V3 and Vk plus M. More than K or K vertices. And here we have some vertices. Now we have to find, now we are given that this graph G is K connected. This graph G is K connected. And we have to ensure that we can find ST paths, disjoint ST paths. That is a path which is one endpoint is in S and one point in T, and they should not intersect. So what Menger's theorem talks about disjoint paths, UV disjoint paths. That is disjoint paths. That is, instead of sets we have vertices here. So how do we rectify this situation? Menger's talks. So how do we rectify this? So what we do, we consider a new graph G dash. Consider new graph G dash with two more vertices such that consider G dash such that vertices of G dash, we add two more vertices. So we add one vertex X and add one vertex Y such, and what are the additional edges? We are connecting it with each of the vertex here. And edges EG dash is equal to EG union X VI for all VI in S union Y WI all WI. So now any XY path will give us a ST path after removing X and Y. So from Menger's theorem we have number of disjoint XY paths is equal to maximum number of minimum is equal to maximum number of disjoint paths. Okay, I mean to say, from Menger's theorem we have that maximum number of disjoint ST paths is equal to minimum number of vertices in maximum number of disjoint ST path, which is equal to maximum number of disjoint XY paths. Okay, sorry. Wait. From Menger's theorem we have maximum number of disjoint. That might, what I was saying previously, that might not be true. Hence, I'm saying this. From Menger's theorem we have that maximum number of disjoint XY paths is equal to minimum number of vertices in separating set of U and V, right? Minimum number of vertices require U and V. Therefore, it is enough to show that therefore it is so we have that maximum number of disjoint XY path equal the minimum number of vertices in separating set of U and V. We want to ensure that we have at least we have k disjoint XY paths. So if we have k disjoint ST paths. So if we can say that we have k disjoint XY paths, if we can show that we have k disjoint XY paths, then we will also have k disjoint ST path. And if we want to use Menger's theorem, therefore it is enough to show that a minimum number of vertices in separating set is greater than equal to k. Because if minimum number of vertices in separating set is greater than equal to k, then we'll have at least k disjoint xy path, and if we'll have k disjoint xy path, we'll have k disjoint st paths, and that was required for us. And now if we want to show that minimum number of vertices in separating set is greater than separating set for xy is greater than equal to k, it is enough to show, therefore it is enough to show that k minus 1 vertices does not separate u and v. Okay, so we want to show this. Therefore now we have reduced our problem to showing that we have reduced our problem to showing that any set of k minus 1 vertices does not separate u and v. So our graph G was k connected. Now what about G dash? Can we say that G dash is k connected? Claim is G dash, yes, we can say that, and this is my first claim that G dash is k connected. Yeah, so this is a, like, we just want to show that k minus 1 vertices does not separate u and v. What we are showing is much stronger, because if G dash is k connected, then we'll get what we wanted to show. So this is much like, we are showing much more if we are showing G dash is k connected. So since we can do that, so I'll do this. But it is sufficient to show that k minus 1 vertices does not separate u and v. So if G dash is k connected, if this is my statement A, we get A and we are done. So now why G dash is k connected? So what we have to do, remove vertices v1 till vm such that m is less than k. Now if we don't have v intersection, sorry, this was v, if this v does not have xy, then it is clear that G prime minus v is connected, because now, okay, sorry, case 1, v1 xy does not belongs to v1 till vm. Then we are removing less than k vertices, so we have that G is connected. Moreover, since S has more, since S has at least k vertices, X cannot be isolated, and neither do Y. Therefore, we see that G prime is also connected because both of them are connected to some vertex of G. And case 2 is, if it is, case 2 is also fairly easy, that if X or Y belongs to V1 Vm, then also from X, then by similarly X, Y, if X or Y is belonging to it, or both of them are belonging to it, G remains connected because we are removing less than k vertices from G, and X and Y are also not isolated. So we get that in both these cases that removing less than k vertices, G prime remain connected. Therefore, G prime is k connected. Therefore, we get that any set of k minus 1 vertices cannot separate U and V, because if any less than k minus 1 vertices or k minus 1 vertices, because it is k connected, so even if we remove k minus 1 vertices, the graph remain connected and we will be able to find a path between U and V. And once we have shown this, then using Menger's theorem, we are done. So this was our last question. Okay, thank you.